Hi everybody, and welcome to our today's online symposium. My name is Julia.
My name is Gero.
We are both from the application team, and we are sitting in front of our facility line and super easy to use STED microscope. And we would like to show you today our new TIMEBOW feature.
Yes, TIMEBOW is for lifetime imaging, and lifetime imaging really became a lot easier with TIMEBOW. And we are going to look into separating lifetime species. We're going to look into lifetime to improve STED super resolution. And we're also going to use the matrix detector, which adds a new dimension to lifetime imaging, really. And that's quite a unique feature we're going to show today. And I think you brought along something as well?
Yes, that's true. I brought living cells with me, and we will go for a session and have a look on multicolor STED imaging with these cells with our new TIMEBOW feature. So let's get started. If you have any questions, please write them in the chat function.
Since I promised you that lifetime imaging is really easy with TIMEBOW, I'm going to keep the introduction to a bare minimum. In essence, we have a pulsed excitation laser that excites dyes into an excited state. From that, they can send out a photon, which we can detect with our single photon detectors, which are time resolved. Why time resolved? Because over time, more and more fluorophores return to the ground state. We get less and less photons being sent out. We get an exponential decay of fluorescence over time. And we're looking here at the nanosecond time scale. When we reach about 1/e of the original fluorescence level, we have reached what we define as tau, or the lifetime of the fluorophore. And this can be shorter or longer for different fluorophores, or one fluorophore can have different lifetimes depending on the environment, for example. For us, this lifetime is also important in STED imaging, because when we look at our normal scanning spot in a confocal microscope, it's rather large. What we use is a STED beam that switches off the fluorophores at the periphery, because it is donut-shaped, and in the center they're not being switched off. That switching off basically leads to a shorter lifetime at the periphery of the scanning spot and a longer lifetime in the center, and this is something we can measure in our microscope. We are not going to use exponential fitting to measure the lifetime, but we are going to use a phasor-based approach, which I believe is very easy to handle, and it can also deal with fewer photons to get a nice lifetime estimate. So let's have a look in the software how the phasor-based approach works. Here we can see an example of a phasor plot and of a lifetime image. The lifetime image on the top shows the typical color coding for lifetime values. For example, the blue areas are areas with shorter lifetimes, while the red areas represent longer lifetimes. In the phasor plot on the bottom, we can see the phasor plot is basically a large semicircle, and in that semicircle we have multiple dots. Every dot represents basically a pixel in the image here on top, and the position of that dot within the phasor plot represents the lifetime value of that pixel. Now, how can we tell what this position exactly means? If we go here and put a time scale to the semicircle, we can see that on the right we have very short lifetimes, and going along the semicircle we go to the longer lifetimes. So every dot which is right on the line here will be a pure lifetime population, while dots which are further in the center will be mixtures of different lifetimes.
Nice. Thank you for the introduction. I look forward to see it in the software. What kind of samples have you brought us?
Well, I've brought along a sample with two dyes, but both dyes are spectrally nearly identical. But with TIMEBOW, we will see if we can separate them into two image channels. So let's get started in the software. All right, let's open a new sample. I will select star red, which we have in the sample. We also have star 635P, but that is of the same color. New overview, and going to live mode. We will see an overview image, and with the mouse wheel I can refocus to get everything nicely into focus. Now when I stop the live mode, I'm automatically presented with a ROY tool. I can select a region of interest here. If I want, I can move it or even turn this region of interest. And now I'm going to select in the scan menu, in the escalation, the matrix detector. When I use the matrix detector, I also open the pinhole because, well, I want to have all the light on the matrix detector, and the matrix detector will discriminate basically what's in focus and what's out of focus. Going back to live mode, I can refocus again using my mouse wheel. And now we'll go to the TIMEBOW menu and activate lifetime imaging for the confocal channel here. Looks the same because the intensity values are the same, but I can open the TIMEBOW display, lifetime and intensity. Now we have intensity information, but also lifetime information. You can see when I change the lifetime lookup table that there's actually shorter lived and longer lived populations in there. Shorter lifetime is the star 635, here the nuclear pores, and the Golgi apparatus is labeled with a star red, which has a longer lifetime. You can also select just 2 colors here for the lifetime, and that basically represents then the 2 dyes here with a nice gradient in between. When I fine adjust this, it really looks like a 2-channel image already. However, I can also open the phasor plot and do some actual separation. So in this phasor plot, we can see on the right short lifetimes, on the left long lifetimes, and 2 populations. Now selecting a line tool, and when I draw this onto the 2 populations, I get 2 images now, and each is labeled with named according to lifetime. I'm changing the lookup table to basically do the same as in the normal lifetime image. But now I actually have 2 channels, so I can separate them out, and you can see that's 2 channels. And if I like, I can optimize the separation here by using this line tool, and I get a live feedback if I'm separating to both populations properly. And now you can see this is a good separation now. And I can, if I want to, also export both images as TIFF, for example, if I want to analyze them separately. So that would be here from this menu. I would like to repeat this experiment now using STED, and that's how I do this. I just drag and drop that into the overview, duplicates the image, and I'm activating STED. Also make the pixels smaller because I'm going to work at a higher resolution now. Also activating TIMEBOW for the STED mode now. I can, if I like to, activate it for confocal and STED, but in this case I only need it for STED. And we can see on the left the confocal image, on the right the STED image. We can see the STED image isn't as crisp yet as we would like it to be. And this is because we're not using time gating here. We are actually now showing all the intensity values. I can do matrix post-processing, and that will remove a lot of the confocal and out of focus background. You can see this now. The top part, you have removed the out of focus light, and the bottom part, it is still just the raw data. Now I can tune this. I can also do some sharpening if I like to. That's the convolution part. The next step, I'll go to the diode chip again, and I will use the lifetime intensity. Again, adjusting the lookup table for the lifetime. I can see there's 2 populations in there. And I can also select again a 2-color scheme here. And then I directly see this is again 2 dyes in there. But now both are shown in super resolution with a higher resolution than the confocal image on the left. Fine-tuning the lookup table a little bit, and I have a really good optical separation now between the 2 dyes. I will now hide our confocal image because I want to make space for a phasor plot. Selecting that from the die chip menu. And I see again two populations here for the two dies. And I can select my line tool and I can draw a line here from one population to the other. Immediately I get two populations which are nicely separated here. I'm adjusting the color tables to match our normal lifetime image here. And we can see that it looks very similar, but again, I can separate this out into two separate images now. And for each image, I can adjust the lookup table separately now. And I can also fine-tune my separation with the line tool. And basically, I'm changing the linear gradient here from one population to the other by dragging and dropping on the phasor plot. You can see you can very easily get an export here as well of the separate images. What I've done so far is I've been using the line tool for separation of my two populations here. I can create nice separate images here. However, I also have another tool that is the circular ROI. So let's select that from our menu. And you can see I can draw a circle, and that basically selects exactly the population I want to have in my image. Sorry. I can move these around, change the size, and I can very accurately crop out one lifetime population here from the phasor plot. However, you also get very hard borders. You won't get a mixture or a gradient. So if you have areas where you have a mixture of both dies in one structure, with this tool you will not really see a mixture. You will see either one or the other population. So that's why I like the line tool.
It looked great. And what is about several color images?
Yes, we have done this with more colors and more channels before. In that case, I used two, not just one color channel. And in each of these color channels, we had two lifetimes, giving us 4 channels in the end. Let's have a look at a few images. Here we can see a confocal image of fixed and cultured cells. We have labeled the nuclear pores and some Golgi proteins with star red and star 635 for channel 1 spectrum. And we have labeled another Golgi protein and actin with star orange and star 580, giving us a second spectral channel. We can separate these two spectral channels easily with our spectral detection, which we call rainbow. But once we add TIMEBOW, we can see there's actually 2 lifetimes hiding in each spectral channel, giving us 4 channels in the end. We can put them together to form one 4-channel confocal image, or when we add STED, we can actually get a 4-channel super resolved image. In this case, we're just using one STED laser. That's a 775 nanometer STED laser, which means we can record this in one go. And it's very easy to analyze it afterwards.
Wow, the 4-color STED images look really good. But what can we do about confocal?
Well, in confocal, we have a few tricks up our sleeve as well. And I think the matrix detector really steals the show here. Let's have a look at a simple confocal image of convallaria, meaning a plant section here. This is an intensity image, basically just the intensity of the autofluorescence of this sample. We can see a few structures, but once we add matrix differential detection, we can see that more structures are revealed, and that's because we are now rejecting autofocus light and we are gaining contrast in this image. This gain of contrast can also be used in lifetime imaging. Let's have a look here. Without differential detection, we can see the color coding for the lifetime in here. But once we activate differential detection, we have again increased contrast. And I think this is a unique combination of matrix type detection and lifetime imaging that I haven't seen like this before. We can also add a few overlays, for example here transmitted light, And of course, we can go and use our phasor plot again. You can see here again a phasor plot, and we have used here circular rows rather than linear rows to separate multiple species, which we can see in false colors on the left.
You already mentioned that you can use TIMEBOW to increase your STED resolution. Can you show that to us?
Yes, I can show that. Mainly when I'm using very, very low STED laser power. Low STED laser power usually doesn't give us the highest resolution. However, that creates very mild imaging conditions for our sample. So it can be useful to lower the STED laser power, and in those cases, TIMEBOW can recover some resolution. Let's have a look. Here we are looking at a confocal image of Kako cells, which are cells that form microvilli. And these microvilli are not yet really visible in confocal mode. When I switch on STED, we can see there's actually a lot of very fine structures in there. But we can also see that there's still a lot of background and out of focus fluorescence. Now, once I add matrix detection to this, I can reject a lot of this confocal background and of this out of focus background. However, now if I also activate lifetime imaging via TIMEBOW, I can also reject more of the low resolution parts of this image, and I gain some additional resolution here. And I think this becomes especially visible in the slightly more crowded areas, and we have very fine structures. How am I doing this? I'm basically using again the phasor plot, and I'm selecting which part should be rejected as it has too low of a lifetime, meaning it has a very low resolution. And that leaves us in the end in the final image with just a very high resolution parts. Earlier I promised that we are going to have a look at living cells, and Julia has prepared some HeLa cells stained for the cytoskeleton. And I'm going to leave microscope control in the hands of Julia now.
Yes, that's right. So I brought a 2-color sample with me here, stained with abberior Live 550 and 590, which are spectrally very similar. Let's have a look if we can separate them right now with TIMEBOW. All right, I will start a new sample and select my dye, abberior Live 590 and 560. Type in my sample name right now here, so live cell, and start a new overview with the new overview button down here. Define the size, and now we are in the scanning mode. I open light path because here I can change the detection window under spectral detection just by pulling it wherever I need it. So, and I also can directly open the pinhole right now here because I will also use the matrix detector for TIMEBOW imaging. In the scan menu, I activate now first matrix, increase a bit the confocal excitation for our overview right now, increase the pixel size a bit and press live, and here we have directly our overview image. So with the hand tool, I can zoom directly in the overview image here with my mouse wheel, which is really nice to find focus. And I think somewhere over here is fine. I stop it, and now I can directly draw my region of interest in my overview. So a smaller region, I can still bring it to the size I need. And now we can scan this one. Settings are good. Also focus plane is quite good right here. So stop it, just copy the image for our STED settings right now. Decrease for our image right now confocal excitation a bit, but increase the one for STED. And I use probably quite a low power for STED, 25%. But therefore increase a bit the line accumulation. Also for confocal. Decrease pixel size to 35 nanometers and decrease the dwell time right now here. Activate TIMEBOW in the TIMEBOW menu by just clicking on STED because we want just to have the STED image in TIMEBOW, so it's just one click. and press scan. And right now, on the left side, we see the confocal image, and on the right side, we see our STED image. You can directly see a good increase in resolution, and because it's a matrix image, I first do matrix post-processing. So use a differential detection of 1 right now here, so I think we can increase it a bit, maybe to 1.3, apply. That looks good. So now the background is a bit reduced, and also in the die chip menu here, we can now open our TIMEBOW menu under the first rider, TIMEBOW display, and select lifetime and intensity right now. So just do it again. And right now we see the intensity plot right now here on our STED image. I use the to color code and start to adapt the longer lifetime, which is here in magenta and staining actine, and the shorter one is in cyan, showing tubulin right now here. So now it's just a bit playing around to find the right settings. So the longer lifetime should be something around 3.3 here. I increase a bit the brightness, and the shorter lifetime is around 2 nanoseconds. So like this looks already quite good. So we see a clear separation between actine and tubulin right now here in our STED image. And with this, we get a STED image on living cells with just one STED laser, and a 2 color separation afterwards with TIMEBOW. Increase a bit the brightness, and yes, looks quite nice.
Yeah, I think that was pretty straightforward using Live 590 and Live 560, right? Mm-hmm. And did you try that with different dyes for living cells as well?
Yes, of course. I did several different combinations. One of them was, for example, Live 610 and the membrane stain DID. Both are in the red spectra, and you can see here an example. So that's HeLa cells, and tubulin is stained with Live 610, and the membrane is stained with DID, and we can nicely see here the edge of the membrane. That's the confocal image with our TIMEBOW, so we cannot separate these 2 channels. But if I did a STED image with TIMEBOW right now, we can easily separate them, show tubulin in cyan here right now, and the membrane in magenta. And also we see a really nice STED effect right now here.
Yeah, I would say so. I can definitely see some extra structures now in the membrane stain. I would say up here, I can definitely see 2 structures instead of 1. And I think the projections are also far better delineated here. And of course, the tubulin appears here as single tubules rather than, say, one big blob here. So I think, yeah, makes a good difference here.
Yes, and because it's such a nice cell, I also did a time lapse from these cells. So that's right now here. Mm-hmm. First the confocal, and right here the STED image. And we can nicely see moving around the tubulin and the membrane stain in these movie right here.
I hope today we were able to convince you of the benefits of TIMEBOW for lifetime imaging. We started today with our phasor-based toolbox, which is easy to use, and we could generate multiple extra image channels just using lifetime separation in confocal, but also in STED super resolution mode. We then moved on to TIMEBOW and matrix in a combination. The benefit here was that we could use rather low STED power, still get a good resolution, and also suppress background with the matrix functions. The matrix detector itself is already beneficial in normal confocal imaging, where we get a higher contrast and higher resolution in our lifetime images. And then finally, Julia showed us some live cell imaging.
Yes, and of course TIMEBOW is an easy tool to have multicolor images in living cells with really mild conditions. And now it's time for the Q&A session, and I get a bit of help. So let's start with the questions. A question about the detectors. Do you recommend to use always the matrix detector for TIMEBOW imaging?
No, you can also use our standard APD detectors. In fact, if you have a system with maybe 3 APDs and 1 matrix detector, you can use all 4 channels for lifetime imaging with TIMEBOW. The matrix detector has one advantage. It gives you sharper images with less background signal when you're doing lifetime imaging. And also you can work at higher detection rates and higher speeds because you're splitting all the photons onto multiple detector fields in the matrix detector. The APDs are also good for lifetime imaging. However, you need a small hardware upgrade to get started with TIMEBOW there.
Okay, thank you. So you can use your APDs, but you need a hardware update, so contact us therefore. Another question about STED and TIMEBOW. So do you recommend to use always TIMEBOW for your STED images?
No, I don't think you need TIMEBOW for all STED imaging. When you're using a very low STED laser power, which usually gives you a low resolution, then TIMEBOW can give you a little bit added resolution at that low STED power. That might be nice if you want to be mild to your sample. At higher STED powers, I don't see an advantage over gated STED. And that's because we're already starting with the optimum setup here. So we're using pulsed excitation lasers and pulsed STED lasers. And that is the optimum approach for, well, lower bleaching, higher resolution. And I think there we are really fine with gated detection.
Thank you. Do you have to do all the analysis on the setup PC?
No, so that would be very annoying in the workflow. So we are also providing a free offline or viewer version of our software where you can do all the TIMEBOW analysis.
It's a great thing. Another question about adaptive optics. So can you combine it? We haven't shown it here, but is it possible?
Yes, of course. You can combine adaptive optics with all our imaging modes, and it helps you to get deeper into, say, tissues and other samples which have a refractive index that's not ideal. So easily combinable, yes.
All right. And what about spectral detection? Is that combinable with TIMEBOW as well?
Yes, spectral detection is combinable with TIMEBOW, and it's also combinable with matrix detection. In that case, the matrix detector doesn't need any additional user input when you're changing or adapting the spectrum. I think we have seen that actually when you were working with the living cells, you were adapting the spectrum. So that's really just drag and drop to change the spectrum. The matrix detector aligns itself afterwards, and you're ready to go and do lifetime imaging with a matrix detector.
Okay, thank you. So you see, TIMEBOW is really combinable with the adaptive optics and also with spectral detection. Another important question about raw data. So is the raw data accessible?
Yes, of course. So during the imaging session, I think I was showing the button to export separated lifetime species as TIFF files. And you can also export the raw data as TIFF files as well. And that includes all your time bins for histograms, for example. Yes.
Great. So all the raw data is, of course, accessible. One more question about the matrix detector. If people already have the matrix detector in their system and they want to start with TIMEBOW, what should they do?
Well, they don't have to do anything to their hardware, because if you have a matrix detector in your microscope, you're ready for TIMEBOW and lifetime imaging. What you could do is you could just contact us for a software test.
Yes, wow, these are great news. Thank you, Gero, for introducing TIMEBOW to us, and also thank you for the Q&A session.
Well, thank you for bringing along some living HeLa cells and showing us how you can image them.
Yes, of course. And also thank you for your time and for joining us to our today's online symposia. If you are interested in our microscopes or in testing TIMEBOW, just contact us. And with this, stay healthy and see you soon. Goodbye.
Bye.